Unmute. There we go. Awesome. Just like.
Okay, so we'll be talking about missing data today. Whoa.
Sorry.
Yeah, so missing data is everywhere. I'll give an example from like my line of research, I guess. So in my current lab and in my old lab, we would collect fMRI data. fMRI stands for functional magnetic resonance imaging. It's basically a way of measuring blood flow to the brain and seeing what different regions of the brain respond to different stimuli. And an fMRI, an image is taken of the brain every 2 seconds, but not all these time points can be used. Because if someone moves in the scanner, then the data quality is really poor. And so in that case, the data is missing for like these 2 time points. And this is particularly prevalent when you're dealing with participants who love to move a lot. So now that we collect infant fMRI data. And so I was working with a really messy data set where the babies were moving all the time. So this guy, William Shadish, said that one of the most important statistical and design problems in research is missing data. And missing data is everywhere, so how do we deal with it? This is me in lab 7, and I'm just dropping all the missing data, which is a bad thing to do. The American Psychological Association says that deletions are among the worst methods available for practical applications. And this is, it's not really our fault, is what the reading says, because R and Python and other software packages make it incredibly easy to remove missing data.
They do it by default. So we do it a lot.
Yeah, so deletion is one approach to missing data, and there are 2 types of deletion. The first is listwise deletion, where you can discard all missing data from your analyses. This is bad because it reduces the sample size a lot. And that causes a reduction in the power of your significance tests. And then pairwise deletion is where you just discard the incomplete cases on a analysis by analysis basis. So this helps preserve some power, but it's still pretty bad to do. Both of these bias your estimates. And then there's single imputation, and this is where we fill in missing data with replacement values. So we kind of we try to infer what the missing data would be, and there are several ways to do that. One is to just replace the missing data with the mean of that incomplete variable. The other one is regression imputation, where you take where you try to predict the missing values, and here the complete values serve as the predictors and the missing values serve as the predicted values. And we can think of regression imputation as essentially like borrowing information for the missing values from the complete values. But this is a little bit problematic because it assumes like a correlation of 1 between missing values and complete values. And so a more conservative imputation technique is stochastic regression imputation. And this is essentially the same as regression imputation, but instead you're adding random noise term. And this serves as like a residual, which essentially adds variability to your data. And so you're no longer assuming a 1-to-1 mapping between complete and missing values. Yeah, this is also bad because it attenuates estimates of correlation and variability. Yeah, so although these methods deal with missing data, they do so in a pretty naive way and under very strict assumptions. The first step to understanding what these assumptions are is to ask ourselves, why our data is missing. Wait, what happened? Oh. Okay. So Donald Rudin asked himself that question in 1976, and he decided that not all missing data is the same. There are basically three missing data mechanisms that Rubin came up with: missing completely at random, missing at random, and missing not at random. We're going to dive into what all of these mean. But essentially, how do we know which one of these mechanisms apply to our data? This is actually a trick question because the same data set can have all three mechanisms present. It just depends what your analysis is doing and what variables you're using. So the first is missing completely at random. So as the name implies, missing this is not systematic in any way. So the reading described this in a pretty intuitive way, I think, where they said that the observed data can be thought of as random subsample of the hypothetically complete data. So an example of this is if you have a student in a school and you're measuring math scores. If you're not able to collect their math score because they moved to another school and the reason for their move is completely unrelated to like their demographic information or anything like that, then they're just missing completely at random. So like Nicole today is someone who's missing. Like if someone came here and took a survey of the room, then that's a case where we would have that happen. Other examples are scheduling difficulties. So if someone has like a doctor's appointment or something and they can't respond to a survey. There's some administrative issues, like there's some loss of information between data collection and data entry, or sometimes missing data is actually part of the research design. And this is if like certain data collection methods are very cumbersome to the participants, then sometimes researchers decide to like intentionally miss data so that doesn't put like a burden on the participant. This is the strictest assumption of all three mechanisms because it assumes that there is no, that missingness is completely unrelated to the other variables in the data set. Also, if anyone has questions as I move along, please feel free to interrupt me. Missing at random, this is where missingness is related to other measured variables in the analysis, but not to the underlying values of the incomplete variables itself. So the name here is a little bit misleading because missing at random actually doesn't imply randomness at all. In other words, like missingness is systematic. So it means that the likelihood of that your data is missing is probably related to some other variable in your analysis. And that implies like a correlation between the missing data and the other variables.
So just to chime in here, everyone hates these terms. So instead of missing at random, we usually phrase it as conditionally missing at random, which makes more sense than missing at random. But yeah, so some of these terms need a little work, and they're frustrating. But yeah, so we'll usually say CMAR or conditionally missing at random instead of missing at random.
Yeah. And so an example of this would be like if you're looking at substance abuse and its effect on self-esteem scores. If you're measuring that in schools, typically students who have low self-esteem or are engaging in substance abuse might not come to school, so then they can't answer your survey. And so there is this indirect relationship between between the missing data and self-esteem scores because you're not able to collect the full sample. This is a less strict assumption than MCAR, which is what we previously spoke about, because here you're not assuming that the missing variables are completely unrelated to all the other variables in your data. And then missing not at random is the last of the three mechanisms. Here, the missingness is systematic, like MAR, and it's related to the hypothetical values of the incomplete variable. So this is like staying within the incomplete variable itself. So this is like if you're taking a reading test and you're measuring your score on the reading test. If participants don't understand the text excerpt, then they can't possibly respond to the questions. So their score is directly affected by the fact that they can't understand the exam. Yeah, so these are the three mechanisms. Unfortunately, there are, it is only possible to empirically test the MCAR assumption. So a lot of methodologists have found several ways to do this, but we won't go into them today. And there is no way to verify that your data is MAR or MNAR. So as you might remember, MCAR is the strictest assumption, and deletion and single imputation assume MCAR. So that is why they're especially bad to use. Today we'll be looking at two methods that fall in this orange shaded part here. And this gives us a little bit more flexibility because the assumptions for MAR are a little looser. So the first one is multiple imputation, and the second one we'll be looking at today is maximum likelihood estimation. So in multiple imputation, you assume that your data is MAR or CMAR, I guess. Or wait, no,
CMAR, yeah.
CMAR and MCAR. And another assumption is multivariate normality. So how we do this is we fill in, imputation means like filling in the values. So we create multiple copies of the data set. And we carry out the analyses on each separate copy and then pool our results together. So this happens in three phases. The first phase is imputation, where you generate different copies of the data, each with different set of imputed values. This is good because unlike single imputation, we're not putting like all our eggs in one basket and are accounting for uncertainty in missing data values. Analysis, the analysis step is we use the different copies to get multiple parameter estimates and their standard errors. And then pooling, we combine the results from the different copies. So kind of delving deeper into this process.
So you could probably skip this part
Okay.
since I'm going to go over this when I take over.
Cool. Okay. Yeah. So I don't know. Here I'm like talking. Should I talk about this?
Yeah, so you can talk a little bit about this and then maybe just kind of briefly go over maximum likelihood and then I'll take over.
So as I mentioned, you create multiple copies of the data, then you analyze each copy separately and obtain like a multiple parameter estimates. And then you want to pool these parameters together. So if you're estimating the mean, for example, you would take, you would average over all your parameter estimates, and then for standard error, that's a little bit more complicated because there's standard deviation. There's variability in the imputed data sets themselves, since they all have different values for the imputed data. But also there is variability within the estimated parameters themselves. So what you want to do is basically combine the within imputation variance, which results from the difference in imputed values, to the and the between imputation variance, which results from the different parameter estimates. And R has a nice way to do this with the MICE package, which I assume we'll probably be talking about today. Approach number 2 is the maximum likelihood estimation. So this also assumes MCAR and CMAR, as well as multivariate normality. And rather than filling in the missing data here, we're seeking to identify the population parameters that like gave rise to our data. So like what produced the sample that we're working with. So I revealed the answer, but it's okay. So we use log likelihood to quantify the distance between the observed data and the parameters of interest. And the goal is to minimize these distances. So this is conceptually similar to OLS, where we're trying to minimize distance. This looks very complicated, but we can kind of walk through what's happening in this equation where we're trying to minimize the distances, or in other words, maximize the log likelihood estimate. So this term here is the probability distribution function of the normal distribution. So this basically describes the normal curve. Then we're adding all the relative probabilities to get the sample log likelihood. So this is the probability of drawing the entire sample from a normally distributed population. And then the most important term is the z-scoring term here. Basically what you want to do is you want to find the parameters that will give you your data set, essentially. And so what you're trying to do is substitute different parameter values in this term. And this will ultimately minimize the distance or maximize the log likelihood. So how it does that is a score closer to the mean, as you can see, would cause a smaller z-score since the numerator is shrinking. And this would ultimately cause a larger log likelihood. Yeah, so since the population parameters are unknown to us, we audition like different parameter values by substituting them into the function, and then see which ones produce the largest sample log likelihood. Okay, finally, another way to kind of like fortify these methods is to use auxiliary variables. These fine-tune like the missing data approaches by increasing power and reducing bias. And these are variables that are related to our variable of interest, but do not directly answer the research question we're trying to answer. So usually these will be highly correlated with the incomplete variable. So if you're looking at like 12th grade math exam scores and you have a lot of them that are missing, but you have their math scores from 9th grade, then you might use those to like predict or fill in the 12th grade math scores.
So we'll usually use auxiliary variables if the mechanism is not missing at random. Really, that's the only thing that we can do is try to figure out ways to make the data MAR missing at random. So we might introduce auxiliary variables or correlated variables to make our missingness missing at random or conditionally missing at random and not missing at random.
Yeah. So that's it. That's my final slide.
Awesome. Thank you, Ari. And then we'll come back at the end if you guys have questions, or I don't know if you have any questions that you would like to ask, but we can get back to that. So let me share my screen now. And then if you could also send me your presentation so I can post it.
Oh, yeah.
Awesome. So thank you, Ari, very much for that nice introduction to missing data, covering the Enders chapter that I wanted you guys to read, or the Enders article that I wanted you to read. So what I wanted to do with the second half of class is talk about missing data mechanisms and how we can perform these things in R, and kind of walk through an example data set. So hopefully that will kind of solidify some of these concepts. So Ari, I did a really great job of introducing things like MCAR, MAR, and NMAR, but I want to reintroduce those terms just so we understand what those are, because they're vitally important for missing data analysis. I then want to talk about screening data for missingness using an example. I want to talk about diagnosing missing data mechanisms in R, and also missing data methods in R, which Ari touched upon. So list-wise deletion and case-wise deletion. I want to talk about single imputation methods as well as multiple imputation, which is kind of the state of the art. And then I also want to talk about maximum likelihood a little bit in terms of like, how is it imputing those missing values, right? It's implicitly doing that, not explicitly. And then I want to talk a little bit about how to report missing data in our papers, which we often forget to do. So I think it's important that we are able to describe our missingness in our data set. And then this meme came on my Twitter timeline yesterday from Richard McElrath. I don't know, hopefully you guys have seen the movie Terminator. If you haven't seen the movie Terminator, that is your homework for this week, is to watch Terminator. But yes, never replace missing values with 0 in your data set. That is not a good practice. And additionally, you shouldn't use -999 or 666 or some other numbers like other programs use. So today we're going to jump into what's the appropriate way to deal with missing data. So if you've delved into the missing data literature, you've probably encountered the name Donald Rubin. So Ari presented a picture of him on Zoom, I guess I would assume, which is amazing. But he's done a lot of the foundational work in missing data theory. And a lot of what we know about missing data mechanisms have come from his work. And Donald Rubin suggests that a data set can be partitioned into 2 components or 2 pieces. We have the observed part of the model here, so our observed values. There's also a missing part of the model as well. And what we can do is we can combine these 2 things and create what are called missing indicators on each of our variables. So this is what M1, M2, and M3 are. And usually what we'll say is 0 means that it's a complete case or an observed value, and a 1 means that it's missing. And what our jobs are as statisticians, as researchers, as individuals engaging in research is to determine why the data is missing. So why do we have 1s in our data set? And that's what I love about statistics, is because we can act or kind of act as a detective and try to figure out why these things are missing. So that's essentially what our job is. And so Donald Rubin did a lot of work on missing data mechanisms. And as Ari pointed out, these are just different ways in which the data relate to non-response. And these can be completely random, so they can be non-systematic, or they can be systematic. Determining the missing data mechanism is vital, because that will determine what statistical method we use. And if we use the wrong mechanism, it's possible that our results are biased. So we need to really take real care in trying to figure out what the missing data mechanism is. So what does it mean for the data to be missing completely at random, or MCAR? Well, it means that the probability of missingness is unrelated to the data. So we know that a data set can be decomposed into 2 parts, right? So the observed part and the missing part. If it's MCAR, it means that it's unrelated to the observed part and it's unrelated to the missing part. So the probability of missingness doesn't affect the actual probability in the actual data set itself, right? So it's purely random missingness. And as experimentalists, we probably have encountered MCAR data before, right? So if you're running an experiment, let's say the keyboard sticks or something, and it doesn't record reaction time for some of the trials, that would be an MCAR mechanism. And there's a whole host of other examples as well. So what does it mean to be conditionally missing at random? So looking at our model here, conditionally missing at random means that the missingness is not related to the unobserved values, but it is related to the observed values. So what does that mean? So let's say we have an NA for Y2. The reason why we have this NA is related to some of the other variables in our data set. So the reason why we have an NA here might be because of something, or the question for Y1, right? So if we can make the case for this, then we have missingness that's conditionally missing at random, or CMAR. And then we have not missing at random data. So what does it mean to be not missing at random? It means that the probability of missingness is related to the unseen values themselves. So as we see here, right, the NA that we have here is directly related to Y2. So it's directly related to the variable itself. That is why it is missing. And this is probably the most complex missing mechanism and really the hardest to deal with. And I'll talk a little bit at the end about how we can deal with NMAR data, but it's not going to be pretty. It's going to require a lot of work. So do we kind of understand the 3 different missing mechanisms for the most part? Yeah, Ham?
So for example, we have task. So that's kind of like if it's in a more difficult condition, people tend to miss the data more. So that would be something like NCAR.
So that would probably be NMAR, right? Because the reason why they're missing data on that is because it's difficult and they can't do it, right? So they're not completing it. So it would probably be not missing at random, right? So if it's related to the actual variable itself, then it would be NMAR.
But we do record the difficulty condition as a data. So you
Yeah.
record data, right?
Yeah. So if you have that data, then it's not missing at random, right? They just tend to do worse in that condition versus the other condition, right? Yeah.
Assuming we do have that
Yeah.
data,
Yeah. Yeah.
If we
Yeah.
don't, then it's
So if you have the data, it would be CMAR, conditionally missing at random, right? Because you have data that relate to it. Yeah. So like you know why the data is missing, right?
right.
Because it's really difficult. So you have that mechanism, right? So NMAR is we don't know why that data is missing, right? It's something unobserved, right? And we're trying, what we want to do is we want to introduce those variables that can explain it for us.
It could be both.
Yeah.
Like randomly.
Oh, yeah.
Oh, I just in a blink.
Yep.
I missed the data.
And that would be like,
because it's more difficult.
yep. Yep. So we can see how these things can be really confusing and difficult, and how maybe it's just not one mechanism at play, but it could be multiple mechanisms at play. But so what I want to do is I want to kind of take a data set and kind of explain how we can deal with missing data, right? So I want to couch this discussion within a particular data set. So Enders, in his 2023 book, which is kind of the Bible on missing data analysis, if you guys are interested in missing data, I can scan some of the chapters for you. It goes into kind of the state of the art on missing data analysis, but he uses a data set. And I think it's a data set that he completely made up, but that's okay. There's 275 participants, and there's a whole host of different factors that he's looking at. These are psychological correlates of chronic pain. And what we're going to be interested in are two variables from that data set. We want to look at depression, and we want to look at perceived control. So how does low perceived control of pain relate to depression scores? And conversely, how do high perceived control of pain relate to depression scores? So those are the two variables of interest. In the data set itself, perceived control is complete, so there's no missing data, but depression scores are missing. And I've manipulated the data set so that the mechanism is known. So I modified the data set a little bit. So we can actually read in the data set. So let's just go to R and just read in the data set. So I had to do a little bit of data wrangling, and I had to clean up some of the columns because they were just labeled generically as like V1, V2, V3. So that's what this code is doing here. So let's just go ahead and just run this. And additionally, what I did here is I created a variable called this rmarlow, and I said if the control variable is less than 15.51, I'm going to assign it a 1, and if it's not, I'm going to assign it a 0. And then for the depression variable, I basically said that if the MAR low is equal to 1, then we're going to put an NA for the depression score. And then if not, we're just going to leave it as is. So given this, what do you think the mechanism of missing this is in this data set that I've created, given what we know about the mechanisms? So how is missing this related to anything? So I've essentially created a situation where missing this is related to low control. So if you have low control of pain, I'm creating a missingness mechanism. I'm creating an NA, right? So that data is NA. So if you have low scores of depression, or excuse me, if you have low control scores, then you're more likely to be missing depression scores, right? So what mechanism of missingness is that we just discussed? It's in the variable name. What?
Missing at random.
Yeah, so it'd be missing at random, right? So missing at random is where we can take the missingness and correlate it with some other variable in our data set, which here it's correlated to low control. So let's go ahead, and if we just run the data, we'll probably get something that looks like this, or you should get something that looks like this, a data frame. So I've included some other variables too, just because depression on control is kind of, it's not a lot. So I've also added things like age, and I've also added stress. But I want to highlight that in R, missing datas are usually denoted by NA. So we see here on depression, we have NA scores here.
How do we figure out like what the missingness is correlated with if we didn't already know?
I will talk about that. Yep. So that's coming up. So as a first step, before we get into that, we want to look at our data, right? So anytime you have data set, you want to look at it, and we need to identify missing data as our first part. So we can use descriptive statistics and figures to help us answer these questions. What variables have missing data? What's the total amount of missingness? And how much missingness is there by variable? And there's a whole host of different packages that you can use to look at this. What I wanted to do is highlight a package that I like. It's from the NANI-R package, which is a play on words of Narnia. All package creators are just geeks. But I particularly like this package name. And there's a function from this library called vismiss. And you could just feed in your data set to it, and it'll output this nice looking graph here. And this gives us a lot of important information. So it gives us how much is missing per variable. So if we look at the depression variable here, it's missing about, 28%. And that's denoted by these horizontal black lines here. That's missingness. But it also tells us how much missing there is overall. So there's about 5.6% missingness. And then also how much total complete data we have, which is about 94.4%. So this gives us a lot of our data, or a lot of our descriptive statistics. There's another package that I like called skimr, and there's a skim function, and this will output a table, and it gives you your variables. It gives us the number of missingness. It gives us the complete rate, and it also gives us some statistics on those variables. And what I really like about this particular function is that it gives you these cute little histograms for each of the variables. So these are a few different packages that can give you some descriptives on the missingness in your data. Do you guys use any other packages to do this type of stuff? I know people have the packages that they like, and they tend to use them over and over again. What was that? Okay. So use whatever package that you like to do this type of stuff, but make sure that it gives you those important descriptives on missingness. So in addition to the descriptive statistics that we get, right? So total overall missingness, the missingness by variable. We also want to talk a little bit about what are called missing data patterns. And this is basically the structure of observed and missing values in the data set. Essentially, these missing patterns tell us where the data is missing in our data set. And let's just go back to R. So this is here where I want to introduce the MAR, the mice package. And there's a function called MD pattern that will basically provide two things. It will give us a data set of the missing patterns in our data, or excuse me, a data frame with the missing patterns, and then it will also give us a visualization. I'm not a big fan of this particular function. Instead, I tend to use the function plot pattern from ggmice. I think that it provides a nicer visualization, and it gives you more data and more, it makes more intuitive sense to me at least. So let's run that. So this gives us a nice little visualization here, very similar to the mice package. But what I want to do is I want to go over how you read this data matrix here. And what I like about ggmice is that it actually has intuitive axes titles. The mice package does not have these. But essentially how we read this is at top, we have our variable name. So we have ID, age, control, stress, and depress. On the left-hand side, we have our patterns. Each row is a particular pattern in our data. So here we have two rows, so we have two patterns, missing data patterns. The numbers represent the number of observations within those patterns. On the right-hand side, we have the number of missing entries or number of variables that have that missing pattern. And then on the bottom, we just have missingness per variable, right? So depression, stress, control, age, and ID. Looking at our data, if we look at the patterns, we have 2 missing data patterns in our data. The first missing pattern has 198 entries and it's missing 0 variables. So we have complete data for 198 observations in our data set. So complete data for ID, age, control, stress, and depress. The second data pattern consists of 77 observations and missing 1 entry, or it's missing 77 observations are missing on 1 variable. And we can see this highlighted here by the red. And so there's missingness on depression. So that relates to our descriptives that we calculated, right? There's 77 missing observations on depression. Those are our 2 missing data patterns in this data set. And what I've done here too is also included kind of a visualization description of how to read this pattern here. Again, this has more missing data patterns than our data set does, but this gives a good description of how to read this missing data pattern matrix. So we want to report this, and there are several different types of patterns that we can report. So we can group our missing patterns into a univariate type of pattern where we have 1 missing data point, right? So that's what we have here, a univariate missing pattern. There's monotone missingness, where the patterns in the data can be arranged. This is common in longitudinal type studies, where if an individual drops out, the amount of missing data increases. So we can see this kind of monotone increasing pattern. And then there's also non-monotone missing pattern, where the missingness of 1 variable doesn't affect the missingness of any other variable. So we might see kind of islands of missingness in our data set. This is kind of random missingness, where there's not exactly a pattern. And there's kind of several other different patterns that we could observe. I don't do a lot of missing data, analysis stuff. I know that missing patterns are important to report in our data set, but this doesn't tell us what we really want to know, and that's why the data is missing. This just tells us where the data is missing, and we should report missing patterns, in our write-ups, right? By reporting how many missing patterns we have in our data, where the missingness is. But if we want to know why the data is missing, we have to put on our investigation hats and we have to try to figure out why the data is missing, right? So we need to play the game, is it MAR or is it MCAR? Which is based off of the Is It Cake show on Netflix. Does anyone watch Is It Cake? Yeah, I love Is It Cake. So we have to figure out, is the data MAR or is the data MCAR? So we can make the case for MCAR, that our data is MCAR, and there is a test that we can perform called Little's test. And Little's test is basically just a chi-square test, where we can read in this package NANIR, and there's a function called MCAR test. We can read in our data set and it'll give us a chi-square statistic. If that p-value is less than 0.05, right, that means that the data is not MCAR. If it is significant, we say that the data is MCAR. So this could be one piece of evidence in determining if something is MCAR or MAR, but it shouldn't be the only piece of evidence. And a lot of recent scholars suggest that we should not even be trying to test for MCAR. That is a futile effort. And there's a couple of reasons for that. One is more practical in nature. So in the real world, we know that things are highly interconnected to one another, right? Everything is correlated with everything else. So to say that something is MCAR is saying that things are not correlated, right? So that's not really realistic. So they're like, we shouldn't even be testing for MCAR. The other is statistical. So basically we're trying to prove the null here, and we're using a frequentist framework to do that, which is problematic, right? Because lack of evidence doesn't mean, proof of evidence, proof of lack of evidence in this frequentist framework, right? So we're trying to figure out an MCAR mechanism from a whole host of different alternatives, right? So really, it's a futile effort to do this. We shouldn't be trying to test for MCAR. Instead, we should be trying to make the case for MAR, or missing at random, right? So that's what our job is going to be, is to try to determine that our data is missing at random. And there's a couple ways we can do this. So essentially what we're doing is we're comparing our variables and comparing those variables to missingness. So how do those variables relate to missingness? And one way we can do this is use the final fit package. And there's a function called missing pairs here. And I really love this particular function because it outputs these nice little box plots here. If we have categorical variables, it'll output bar plots. But here we specify our explanatory variables, which are control and age, and then our dependent variable would be depression, right? So how we can read these, so in the columns, what we have is the box plot for our variables with missingness not taken into account, right? So these are the variables. Missingness hasn't been removed. What's the median of our variable? The rows is what accounts for the missingness. So if we have missingness, you'll see these gray boxes here. And this is after missingness is accounted for. So what is the median of the variable after those missing data have been removed, right, on depression, right? So what we try to look for are discrepancies in the box plots. So we can see here that there is a discrepancy between these two, right? So we see that the median is a lot lower when missingness is removed from our data set, right? So that suggests that there's a relationship between control and depression. We don't see that same discrepancy when we look at age. We see that the medians are fairly similar to one another. So we would suggest here that age is probably not related to missing depression scores here. But again, this is a visualization. We need to test this statistically. So how do we do that? So what we do is we create, for every missing variable that we have, we create a dummy coded variable, where if there's missingness on that variable, we score it a 1. And if it's not missing, we score it a 0. And I've done that with our data set here. So I've created a variable called depress1. So if depression is missing, I'm going to assign a 1. And if it's not missing, I'm going to assign it a 0. And we can see here in the data set that now we have a column called depress_1, and now it is dummy coded, where 1 is missing and 0 is not missing, right? So now what we have to do is we have to test this statistically. So we can perform a linear model, we can perform a t-test, we could perform a logistic regression. We can do all of those things to test this relationship. Here, I'm just using a regular linear model where I'm using the depression dummy coded variable to predict control scores. So I fit this linear model, and then this is the model output here. So this is our regular summary statistics, right? We have an intercept value. So this would be the mean of control where there's no missingness. And this would be the difference in the mean score when missingness is taken into account, right? So what we see here is that there is about a 5.66 decrease in control scores when missingness is removed from our data set. And this is statistically significant here. So these are the type of relationships we're looking for, right? So statistically significant relationships to prove, I wouldn't say prove, but to make the case for the missingness at random assumption or mechanism. And given that it's statistically significant, it looks like missingness on depression is related to control. So we have a MAR mechanism here. Awesome. That's what we want. So now that we've established a mechanism, what do we do? So I want to first talk about how we deal with MCAR data, because that's the simplest. And then I want to switch focus and talk about MAR data. So probably one of the most popular techniques to deal with MCAR data is listwise deletion. So I already talked a little bit about this, right? So we have missingness in our data set, like NA on depression. What listwise deletion does is just deletes that whole row. That whole row is not considered anymore. And we can use drop NA or NA omit if you like base R. But what we can see here is that row 1 has been completely removed from the data set, right? So it's no longer going to be considered for the analysis. So there are some pros to using listwise deletion. So if their mechanism is missing completely at random, then our estimates are non-biased, which is good, right? So it doesn't matter if we throw that out. But if we perform listwise deletion and there's MAR in our data, it's going to be biased. And unfortunately, we use listwise deletion way too frequently and without establishing a mechanism first, which could be problematic. So we really need to think about why the data is missing. A con of listwise deletion is that it results in lots of data loss. So we reduce power. We might take a data set that has 500 rows and condense that to 50 rows, right? So we're just throwing away lots and lots of data. So not the best technique. As an alternative to listwise deletion, there's case-wise deletion. So here, we're only deleting observations if they're involved in that comparison. So for example, if we're looking at depression and control, right, we would delete this row for this comparison. However, if we were going to look at stress and age, we would keep this particular row in, right? So we can see a lot of benefits for case-wise deletion where it avoids data loss, right? And similarly to listwise deletion, if the mechanism is MCAR, then our estimates are non-biased. But if it's not, then it's biased. But case-wise deletion is not used a lot because what we're doing here is we're making these comparisons on not completely consistent or comparable observations, which is not ideal. So this is not used as much. So those are two methods that we can deal with MCAR data. And now I want to switch focus and talk about how we deal with missing at random data. So luckily, the methods that we can use for MAR data can also be used for MCAR as well. So we should probably be using these methods and not listwise deletion in our analysis. So a very popular technique that I think is widely used still today, especially in survey research, is mean imputation. And I want to highlight why mean imputation is bad and you should not use mean imputation. So essentially what mean imputation is you take a vector, right, with missing variables or missing values. You get the mean of that variable, excluding those missing values. And then what you do is you take that mean that you got and then you just impute it into the data set. So we've done that here where I've replaced these NAs with the mean of the variable, which is 5.33. So I've done some mean imputation here. So why is mean imputation bad? It reduces the variance of the variable. So I have that highlighted here where we can take the standard deviation of the variable without the NAs in, and we get a standard deviation of 2.52. If I look at the standard deviation of the imputed data set, the standard deviation is 1.78. So we see that the variance has been reduced here. So if we're doing comparisons, that is going to increase our type 1 error rate. Which is bad. We do not want to do that. So because of this, because it creeps in bias, we don't want to use mean imputation. There are better methods for us to use. One of those methods is conditional imputation or regression imputation that I think Ari did a nice job of explaining. Essentially what we're doing here is we're performing a regression where we're taking our variable, so control, and regressing it onto depression. And essentially we're taking that equation that we get from there to predict the missing values, right? So we have our regression equation with our intercept and our slope value. We have control values, right? Those are complete. So I can input something like, I don't know, let's say our control value was 10.51. I can use that to predict what the depression score would be, right? So we use values that fall on this regression line right here, right? So this is an unrelated example, but I think it highlights what I'm trying to argue, where the actual values, the missing values, fall on the predicted line, right? We're using that equation to get predicted values. And this could be easily done with the mice package. There's a method called norm.predict that will perform this type of imputation. And I'll go over some of the arguments in a bit, but this is how you would do this in R. But as Ari nicely put it, this does not include the error associated with the model, right? We're just getting the predicted values that fall on the line. There's no error associated with it. So as an improvement over this, we use stochastic regression, which adds variance to the predicted values. So we can see here now that these missing values, right, do not, or the predicted missing values don't fall on the line anymore, right? There's been error that's been added to them, right? So they're kind of further away from the line, right? So this adds some uncertainty to the imputed values. If we wanted to perform this type of imputation, we can use the method norm.nob from the mice package to perform the stochastic regression. So these are popular single imputation methods, but really the state of the art in missing data analysis is multiple imputation. So we really don't use single imputation methods anymore. What we should really be using is multiple imputation. So with single imputation methods, we're only replacing the NA with one value, right? That's the true value. That ignores uncertainty and variance. So what multiple imputation does is it uses multiple values. And in a nutshell, what multiple imputation is just conditional imputation, regression, done several times. And there's several steps that I want to highlight. So in the first step, what we're going to do is we're going to create imputed data sets, and we're going to use the mice function to do this. So I have an example here, right, where we have our original data with NAs in it. What we're going to do is we're going to fill in those NAs with values from our data set, which is important, right? From our data set, not predicted values, but values from our data set. And we're going to do this multiple times. So it's recommended to do about 20 imputations. So we're going to fill in those missing values 20 times with different values. That's the first step. The second step is to analyze those imputed data sets. And we can use with to do this. So we have one data set, we have our imputed values, we're going to perform regression on this. Then we have our second data set, we're going to perform regression on that. And then we're going to do that all the way to data set 20. What we do after this is we take all of our estimates from each of our analyses and we just pull them together. So we have one estimate, one standard error, and one test, right? And we use those equations that Ari showed. They're called Rubin's rules to kind of pull all of those together. As kind of a summary, right? We have a data frame. We use mice to impute our 20 data sets. We then run regressions on each of those data sets, and then we pull all of those results together and we get a final result. And this is more preferred than a single imputation method because, again, we're basically taking into account this uncertainty, right, of different values that it could possibly be and just pulling those together. So it's more preferable and it's more accurate than just doing a single imputation method. So we have like estimates, right? So you have like a slope estimate for each of them. We just kind of average them together. Yeah, yep. So that's what I mean by pool. So kind of average them all together. So what I wanted to do now is I wanted to highlight how we can do this with a data set in mice, right? So one of the arguments for the mice function is M. This is the number of imputed data sets that we want to use. So I've set it here to 5, but we should set it to 20 in accordance with Enders and other folks. But for just simplicity, we're going to set the number of imputations to 5 because it's easy to deal with. We need to set a seed here because the imputation is random. So each time you run it, you're going to get a different result. So in order for it to be reproducible, we should set a seed, and you can set whatever seed number you'd like. We're going to use this method called PMM, which is predictive mean matching, and I'll explain what that is in a bit. And then print equals false is just not outputting any of the results. And then there's also that max int argument that I had here. This basically is just a number of iterations for the imputations. So basically it's for it to converge. So it's doing this random selection. So you can set the number of iterations you'd like for the imputations. I just usually leave that blank or you just use the default. So let's go ahead and just go back to R and run it. So if we look at the imp object here, there's a whole bunch of stuff there, right? We can see all this stuff. What I really want to look at is just what's imp within imp. And if we look with what's imp within imp, what we see is a whole bunch of objects that are data frames. And we see that we have each of our columns here. We have ID, age, control, depress, and stress. And then we also have for each of the, so for ID, age, control, and stress, we see that there's 0 observations. That's because we don't have any missing data there. right? This is essentially what our imputed values are, or what values were chosen on each imputation. So we only have missing data on our depress object. So if we look at the depress object, right, so imp with an imp for the depression variable, we see we have 5 columns here. These are the values that were imputed into the data set, right? 28, 12, 19 for the first imputation, 26, 7, 23 for the second, and so forth and so on. To get our actual data set out, we can use this complete function, and you can get out the complete imputations, so each of the 5 imputations, so the full data set is returned, or you can just get one of the imputed data sets out. So doing all will give you all of them, right? So we have an object list of 1, so that's the first imputed data set, and then there's 2, and so forth and so on. If you just use complete, it'll just give you 1 data set. So one of the imputed data sets there. So that's how you can get that data out if you wanted to look at it and mess around with it. One thing that I wanted to mention real quick. So we need to be very conscious about what data we're putting into the imputation. So in the mice, I'm putting in this DAT data frame, right? And that includes ID variable. And that's going to be used to predict the missing values. And we don't want ID to be we don't want ID to be put into the equation to create our imputed values. So we need to be conscious of this, and we also probably just need to select the columns that we know are related to the missing values, right? So here again, this is everything that's going into the imputation: ID, age, control, depressed, stress. ID we probably don't want to be in the equation here, so we need to be conscious of that. So the method that's used, or the method that I want to highlight, is predictive mean matching. And in a nutshell, what predictive mean matching is essentially is taking a variable that has missing data, and we're using variables that are related to it to get some type of predicted or expected value. So I think that this particular figure highlights this nicely. So we have A, which has missing values. It has 2 missing values here. And we can get an expected value of A given B and C, right? So we perform kind of a regression, and we can get like these predicted values. What I want to highlight here is that we're not using these predicted values to replace the missingness in A. Instead, what we're doing is we're looking at the expected value for the missing row, and we're finding a donor or something that's really close to it. So here it's 0.62, right? And then what we could do is we can see what the actual value is. So here it's 0.24. And then what we do is we replace that missing value with the closest value, which is 0.24 here. And we can do that too for this other missing value. So here it's 1.20. What we do is we find the closest expected or predicted value, and then see what that actual value is, and then replace that with the actual value, right? So we're getting actual values from the data set, which is preferable, or more preferable than getting a predicted value, which might not be within the range of the data set. Maybe it's negative, you don't have negative numbers, et cetera, et cetera. So this is a much more preferable approach. Yeah, Chris?
How does this approach change when you have nested structure in your data? So these data have like no experimental structure, right?
Yeah.
So you could imagine at different levels.
Yeah, so you can do multi-level modeling. So what you do is you do like level 1, impute your data, and then you have to put in your level 2 variables if you had those. So that's how that would account for it. But basically what it's doing is kind of taking the correlation structure between these variables to see which variables are correlated to one another, and then using that in the imputation method. But yeah, you can input a whole host of different models and account for that type of stuff. So this is kind of a very simplified representation of what this is doing. Again, it uses what's called a donor set, where it's selecting a whole bunch of values that could be related or very similar, and then kind of just placing them in there. And then we're doing this multiple times and then pulling across all of these. But this is what predictive mean matching is, essentially. So after we have our imputed data sets, what we're going to do is we're just going to fit a simple statistical model on each of our imputed data sets. So we can use the width function here, and basically we can input our model here. So here we're doing a linear model. Here we could do a multi-level model, right, with LIMR or LMER. You could do a GLM if you wanted to, whatever. But this is our model where we're using control to predict depression scores. Then if we take that fit object and just output a summary, what we'll see is 5 different regression outputs, right? So it's performing regression on each of our imputed data sets. And that's what we see here. Then what we do after this is we just pool all of our results together using this pool function, this handy function, using those rules that I already talked about, which shows how you can combine all these things. But again, we're just taking the average of all of these. And then we can output basically one summary of our data set. So this is what we would report. And we see that there is a statistically significant relationship between control and depression, right? So for an increase in control, depression depression score is reduced by about 0.51. And this is what we would report. And we get all of our useful statistics here. So in a simple case like this, where we have, a continuous variable, or maybe we only have one categorical variable, using kind of the summary result, generic functions will work. But if we have lots of different categorical predictors and continuous predictors, reading the summary output is kind of difficult. Unfortunately, we can't use m-means with mice objects, or if we can, it's really difficult to do because again, we have all these imputed data sets. So a package that I found that I've been trying to use more and more frequently is called marginal effects. And this allows you to perform hypothesis tests on those coefficients similarly to m-means. And what we can do is we can feed in our model using this average slopes function if we're using continuous variables, average comparisons if we're doing categorical variables, and it'll allow you to do these pairwise comparisons on your data. Here again, we get something similar to our output because again, we only have one continuous variable. So we get our slope estimate, but if we have multiple categorical predictors, it will output the comparisons between those, right? And then we can use that to report, which can be pretty handy to use. So an important step in multiple imputation is to make sure that the imputed data that you have looks similar to actual data, your actual data here. So we want to make sure we plot that and make sure that it doesn't look wonky at all. So here in red are our imputed data sets, and then in blue here is the actual data. It doesn't look too bad. There's nothing really that sticks out as concerning to me. So I feel like the imputation was fairly successful here. There is some kind of missingness in the middle here, but for the most part, this is something I wouldn't be too concerned about. But we always want to make sure that our imputed data looks similar to actual data. All right, so now I want to switch focus. So another method that's used quite frequently is maximum likelihood. So last week we talked about multi-level modeling. Multi-level modeling uses maximum likelihood under the hood. And this is the reason why we can have what's called unbalanced data or missing data, is because of maximum likelihood estimation. So I wanted to kind of go over how maximum likelihood accounts for that missing data. So if we remember, maximum likelihood essentially just finds the best parameters, or the parameters that maximize the likelihood of the data, right? So what's important to note here is that we're using complete data, or all the data that's observed, right? We're not throwing out any data, but we're not imputing any values into the data set. We're not doing something similar to multiple imputation. We're just using the data that the participants have, right? So it's performing what's called implicit imputation, where each participant contributes their observed data. The data are not filled in, but instead, what we use is the multivariate normal distribution. So that's the assumption of maximum likelihood. And we use this as kind of an imputation machine. So given where our observed variables are, we kind of intuit where the missingness lies. And our estimates are adjusted accordingly for that. So let's look at an example to make this a little bit more concrete. So let's take our chronic pain example, where we know that the mechanism is missing at random, right? So participants with low perceived control are more likely to have missing depression scores. So I know the true state of the world, and both means for those variables are 20, right? So that's highlighted here. We have this cross section, it's at 20. If we just remove those missing values, right? So this would be called a complete case analysis. So if we listwise delete this, what we've done is we've biased our estimates now. So the perceived control mean is 23.1 and the depression mean is 17.2 now, right? So we have a biased estimate. So what we want to do is we want to incorporate that partial data that we have. So we have perceived control data, right? That's complete, right? So we want to include that back into the analysis. And we know that the perceived control values that are missing are low in nature. So what happens when we add in this perceived control variable again is that it increases the variable's variability, right? So we're entering in all of these data points for low control. That's going to make the variable more variable, right? So what we see here is that, so the true mean for the both of them is 20, right? So when we include these perceived control, these low perceived control scores, we see that there's kind of a downward adjustment to account for those low scores in the actual true mean. What we can do is we can use maximum likelihood, which assumes multivariate normality, right? Assumes a normal distribution. And we know that in this data set, there is a negative correlation where low perceived control, right? High depression, or conversely, high control, low depression, right? So there's a negative correlation within this distribution, right? So what maximum likelihood can do is basically it intuits where the missing values most likely fall. So the values would probably most likely fall on the tail end here, right? So we know where all the observed values fall, right, within here. So what maximum likelihood does is like, okay, so the values probably are most likely here in the tail, right? So that's where the missing values are most likely located. So what this does is it basically adjusts the estimate to account for that, right? Because we're using this, all the available information that we have about the data set, which I think is just really cool. So we get an estimate that's pretty close to our true mean here. So that's essentially what maximum likelihood is doing in a nutshell and to account for this missing data. Again, it's not imputing explicit values. It's just intuiting those values or accounting for them in some way. So yeah.
So maximum likelihood still just fit on the existing data,
Mhm.
right? It doesn't fit on the missing data.
No.
How is that? I don't know. I still don't understand. How does that help? And how is that dealing with the missing data?
So basically, we're assuming a normal distribution. So we know where the observed data is, right? So basically, where the less likely values are, or where it may be in the tails, that's where it's suggesting that the actual missing values lie. So basically, it's just accounting for it or adjusting for it, right?
How is that different from imputing with regression? Isn't that kind of assuming you have a model? Regression also assumes a normal distribution, right? It's assuming you have a model
Yeah.
from which the missing data is supposed to be generated from.
So regression doesn't account for missing data, right? You have to have listwise deletion, right? You have to have complete cases for regression, regular regression.
But you could just fit the regression on the regular model and run maximum likelihood, which is equivalent to ordinary
Yeah.
square.
You could run maximum likelihood on that. Yeah, that's what essentially it's doing, right? But in general, OLS regression doesn't use maximum likelihood, right? So
Is that gonna give you different estimates?
it should. So basically, yeah. So if you use the regular like LM function, right? So not using maximum likelihood estimation, just regular OLS, right? It requires complete cases. So basically, you're biasing the estimate. Whereas in something like multi-level modeling, you're using all the data that's available, right? And so if there's missing pockets there, it's intuiting where the missingness lies, and they're accounting for basically adjusting the yeah. Yeah. Yep. So there's some issues with maximum likelihood. So it's generally limited to normal data. I don't know of any methods for non-normal data, but they could exist. Yeah.
So in computational modeling, sometimes we just build our own model.
Yeah.
In that case, we specify the likelihood.
Yeah. Yep. Yeah, but if you're just doing regular plain regret, yeah, it doesn't account for But yeah, if you're building your own model and accounting for that, then yeah, you can account for that missing data stuff. And maximum likelihood would account for that. So yeah, you need normal data. The methods that are out there might be some non-normal methods. I'm not sure, but generally limited to normal data. If we have interactions or nonlinear terms in our model, the actual maximum likelihood is biased. And with multi-level modeling, you can only have missingness on the dependent variable. You cannot have missingness on our predictor variables. And the reason why that is because multi-level modeling makes specific assumptions on that dependent variable, right, about the normality of the residuals. It does not make assumptions about the predictor variables. So what multi-level modeling will do if you have predictors with missingness is it will listwise delete them. So not the best. There are more advanced methods like structural equation modeling, which allows you to specify the distribution of the predictors. So you can use maximum likelihood to fill in those missing values. But within multi-level modeling itself, you can only have missingness on your dependent variable, not the predictor variables. But this is how we account for that missingness within multi-level modeling, is kind of using this implicit imputation method, which is maximum likelihood. So with the rest of the time, I wanted to talk a little bit about NMAR data, and I've deliberately not, I've not spoken about NMAR data and how to distinguish it between MAR and NMAR, because really, pray that you don't have to. You don't want NMAR data. It's very complicated. There are some statistical techniques that can deal with NMAR data, like pattern mixture modeling, but it's complicated to implement and it's probably not the best. So what I wanted to do is basically lay out some suggestions. So ideally what you want to do is, if you have NMAR data, make it MAR, make it conditionally missing at random. And I have some suggestions on how to do that, and it's not going to be easy. One suggestion is to track down the missing data. So this is from a Reddit forum from maybe about a month or so ago. This is the extreme case of tracking down data. You should never do this, but basically, grad student forgot to collect some data and basically went on Facebook or tracked down this participant on Facebook to ask for the data. So this is kind of an extreme example of tracking down the data. Obviously, you want to go through proper channels to get the data, but yeah, you should track down the missing data and get the missing data if you can. That's one suggestion. The other suggestion is to include auxiliary variables. So hopefully you have a whole host of other variables that can explain the missingness. So again, transferring it from NMAR to MAR, right, by including in other variables. And you might not have those variables. So what do you do then? Well, basically you have to do double sampling. So you have to collect more data, right? So you have to basically reach out to all your participants and ask them additional questions. So you can make that mechanism MAR, and you can use things like maximum likelihood or multiple imputation. So that's essentially what you have to do when you have NMAR data. There's not really any good solutions for that. So as I said before, missingness is not really reported in the literature, or it's kind of just skirted over. So there's a template from Stefan Bruin, who created the mice package. He provided this nice little write-up that you can use for reporting missing data. So please read this, and also please report missing data in your work as explicitly as possible. I have some kind of overall points that you should discuss, like amount of missing data, the reasons for missingness, the consequences of missingness, the method you use, imputation model, what type of polling was used, the software and packages you used. And also you should include a complete case analysis, so you can compare the complete cases or the listwise deleted analysis with the analysis with the multiple imputation or imputation method you used to compare them to see if there's any differences. So with the couple minutes that we have left, I want to play, is it MAR, MCAR, or NMAR? So let's say that we have a manipulation track questionnaire and 5 participants were accidentally thrown out. What mechanism is that?
MCAR.
Yep, it would be MCAR. Why would it be MCAR?
Totally random.
It's totally random. It was accidentally thrown away. So it has no impact on the actual results of the experiment. So in a 2-day memory experiment, people who know they would do poorly on the memory test are discouraged and don't want to return for the second session. What mechanism would that be?
Not missing.
Yeah, it'd be not missing at random. Why would it be not missing at random?
Because the whole part of distribution is removed.
So it's related to the actual variable itself, right? So people not returning for this memory test because they have poor memory, right? So that's why that data is missing. And then you could track them down on Facebook and give them some survey questions and then make it MAR if you wanted to.
But only record the data from the first memory test. So the first memory test predicts who's missing.
That's true. We could probably use that, right? We could use the memory test from session 1 to see. They might have like low scores, and that could predict why. So it could be MAR. So you can make the argument for it. What about this one? A health psychologist is surveying high school students on marijuana use, and then students who scored highly on anxiety left their questions blank. What mechanism would this be?
Probably non-random.
You're saying, did you say MAR or MCAR?
And more. Because
Hmm.
you don't have anxiety score.
So remember what missing at random entails. That the missingness is related or correlated with other responses or other variables in your data set.
Which is anxiety.
Yeah.
You don't measure it, right? Because you're measuring marijuana.
But we related it. So yeah, this is a completely random example. But the point part here is students who scored highly on anxiety left these questions blank. So we know why that there's missingness on marijuana use, right? It's because people with high anxiety didn't want to respond to that, maybe because they are marijuana users. So this would be a MAR mechanism, missing at random, right? Because it's related. So missingness on marijuana use question is related to anxiety or high anxiety. So that'd be MAR. So as wrap up, when you have missing data, think about the mechanisms of that missingness, because if you don't diagnose that mechanism correctly, you can bias your results. So it's important to think about these things. So the state of the art really is multiple imputation and maximum likelihood. There are also other methods. So Bayesian estimation is also kind of the state of the art. So a lot of people use Bayesian methods, but really Bayesian methods, multiple imputation, maximum likelihood usually provide kind of similar results, but all three are pretty good. There's also other types of methods that you can use, not widely used in psychology. Things like inverse probability weighting. I think that this is more often used in like econ and poli-sci, but inverse probability weighting seems to be a good way to reduce the bias with missing data. And I've included a citation for inverse probability weighting if that's something that you're interested in. But that is all that I have. So Wednesday, we're going to work through an example, and you're going to be applying these missing data methods to a particular data set. So it should solidify everything that we talked about today. So are there any questions about missing data? How do you guys deal with missing data in your work? Or do you just ignore it? List-wise deletion? Well, if you're using multi-level modeling, you're already using maximum likelihood though, so
okay.
I think you should be good. So yeah, no, I'm kind of interested like in machine learning, like what's commonly done. I mean, you have some massive amounts of data. Like, is it just, do you use imputation? Do you just throw out the missing data? That's kind of what I'm kind of interested in, is machine learning kind of applications.
Are you talking about like a generative model or a distributed model?
I mean, like, so in both cases, you'd have some type of missing data, right? Or like there's things that you didn't collect.
Yeah, so I guess one technique you might be able to do is if you feel like if you're doing like a regression, Gaussian process regressions are a very popular method, which gives you like uncertainty bounds around missing data, right? So you have this like measure of epistemic uncertainty. That's one way people do it.
Okay.
In a discriminative setting. In a generative setting,
It's probably already Bayesian, right?
Oh.
Yeah, if you're doing a generative model, then it's probably similar.
Bayesian, okay, so it's taking into account that missing value is interesting.
The distribution of the data as opposed to
Oh, interesting.
like you're essentially modeling like P of X
Yeah.
and Y instead of P of Y to X.
Yeah.
And it's almost never a closed form solution, but
Yeah.
probably always either maximum likelihood.
And then to actually measure things, you use some sort of like Monte Carlo simulation.
Yeah. So yeah, that's what the Bayesian methods are doing under the hood, right? So accounting for the missing value. So okay, that's interesting. Awesome. All right, so I don't want to keep you guys. So if you want to stick around and ask questions, you can. But I will see you on Wednesday. Hopefully you survive the snowstorm. That's tomorrow.